Welcome to this specialized mathematics lecture on polynomials, designed for Class 10 students. Today, we step into the elegant world of algebra to explore polynomials, which are the fundamental mathematical expressions structuring engineering, physics, and computer science. The word polynomial comes from poly meaning many, and nomial meaning terms. A polynomial in one variable, x, is an algebraic expression where the powers of x are non-negative integers. Tracing the classification tree on your screen, observe how polynomials split cleanly based on their degree, the highest exponent of the variable, and their number of terms. A degree of 1 defines a linear polynomial, a degree of 2 structures a quadratic polynomial, and a degree of 3 represents a cubic polynomial. By terms, expressions split into monomials, binomials, and trinomials. Each category structures a unique mathematical model to describe shapes, velocities, and gravity in our universe. Let us define the core concept of a zero of a polynomial, which acts as the algebraic solution or key to any polynomial equation. Conceptually, a real number k is said to be a zero of a polynomial p, x, if and only if evaluating the polynomial at x equals k results in exactly 0, meaning p of k equals 0. Finding these zeros algebraically is equivalent to solving the polynomial equation p, x, equals 0. To illustrate this, let us observe the factorization tree of a quadratic polynomial, x squared minus 2x minus 8, unfolding on your screen. By splitting the middle term, we write the polynomial as x squared minus 4x plus 2x minus 8. Factoring out common terms yields x times the quantity x minus 4 plus 2 times the quantity x minus 4, resulting in two prime linear factors, the quantity x minus 4 and the quantity x plus 2. Setting these factors to 0 reveals two distinct real zeros, x equals 4 and x equals negative 2. Mathematics bridges the gap between symbols and shapes beautifully. Let us explore the graphical method of finding the zeros of a polynomial. When we plot a polynomial p, x, as a geometric curve on a two-dimensional coordinate grid, the zeros of the polynomial are not just dry numbers. They manifest physically as the exact points where the curve crosses or intersects the horizontal x-axis. Why does this happen? At any point on the x-axis, the vertical coordinate, y, is exactly 0. Since we set y equals p, x, any intersection point must satisfy p, x, equals 0. Observing the high-fidelity coordinate graph plotted before you, trace the smooth blue parabola representing our quadratic polynomial, x squared minus 2x minus 8. Notice how it sweeps down through the quadrant and crosses the horizontal x-axis at exactly 2 points, negative 2 and positive 4. These physical intersections are the graphical representation of our zeros. To understand graphical methods thoroughly, let us start with the simplest case, a linear polynomial of the form p, x, equals a times x plus b, where is non-zero. The graph of a linear polynomial is always a monotonous straight line. Because a straight line can cross a horizontal axis in at most one point, a linear polynomial can have at most one real zero. For instance, plotting y equals 2x plus 4 yields a straight line that tilts upwards, cutting the x-axis at exactly negative 2, which corresponds to the algebraic zero of negative b over a. In our left side panel, trace how this straight line cuts across the coordinate quadrants. Its single x-intercept confirms that linear equations possess exactly one unique algebraic solution, establishing a perfect visual algebraic bridge. Next, let us elevate our geometric exploration to quadratic polynomials of the form p, x, equals ax squared plus bx plus c, where is non-zero. The graph of a quadratic polynomial is a beautiful, symmetrical curve called a parabola. Depending on whether the leading coefficient, a, is positive or negative, the parabola sweeps open either upwards like a cup or downwards like an arch. Because a curved parabola can cross the horizontal axis at most twice, a quadratic polynomial can have at most two real zeros. Depending on the algebraic discriminant, the parabola can intersect the x-axis at two distinct points, touch it at exactly one tangent point representing equal zeros, or float entirely above or below it with no real zeros. This geometrical behavior completely defines the algebraic nature of quadratic equations. We now explore the profound algebraic relationship between the zeros of a quadratic polynomial and its numerical coefficients, first discovered by ancient algebraic masters. Let us represent the two real zeros of the quadratic polynomial, ax squared plus bx plus c, as the Greek letters alpha and beta. The sum of these zeros, alpha plus beta, is always equal to the negative of the coefficient of x, divided by the coefficient of x squared, which is negative b over a. Observing the algebraic verification dashboard on your screen, let us verify this relation for our polynomial x squared minus 2x minus 8. Here, a equals 1, b equals negative 2, and c equals negative 8. The zeros are 4 and negative 2. The sum of zeros is 4 plus negative 2, which equals 2. Using our coefficient formula, negative b over a equals negative of negative 2, divided by 1, which is 2. The match is mathematically perfect. Let us now examine the second crucial relationship, the product of zeros. The product of our zeros, alpha multiplied by beta, is always equal to the constant term, c, divided by the coefficient of x squared, which is c over a. Let us verify this relationship algebraically for the same polynomial, x squared minus 2x minus 8, where the constant term c is negative 8 and the leading coefficient a is 1. The zeros are 4 and negative 2. Multiplying our zeros, 4 times negative 2, yields negative 8. Using our coefficient formula, c over a equals negative 8 divided by 1, which is negative 8. Once again, the algebraic formula and the product match perfectly. These two mathematical bridges allow us to verify the zeros of a polynomial instantly, linking the roots of an equation directly to its coefficient structure without factoring. What if we are given the zeros alpha and beta, and we want to construct the polynomial ourselves? Algebra provides an elegant formulation. Any quadratic polynomial whose zeros are alpha and beta can be formed using the equation x squared minus the sum of zeros times x plus the product of zeros. Mathematically, this is written as x squared minus the quantity alpha plus beta times x plus alpha times beta, all scaled by a constant k. For example, if we are given that the sum of zeros is 2 and the product of zeros is negative 8, our polynomial is constructed as x squared minus 2x plus the quantity negative 8, simplifying cleanly to x squared minus 2x minus 8. This allows engineers to reverse engineer formulas, constructing physical curves from desired intersection points. To generalize this beautiful bridge, let us observe polynomials of higher degrees, particularly cubic polynomials of degree 3. A cubic polynomial, ax cubed plus bx squared plus cx plus d, has an S-curve wave shape on a graph and can intersect the x-axis in at most 3 points. Therefore, a polynomial of degree n can have at most n real zeros. In the comparative geometric panels on your left, observe the shapes. A degree 1 linear equation forms a single straight line crossing once. A degree 2 quadratic equation forms a parabola crossing twice. A degree 3 cubic equation forms an S-curve crossing 3 times. This fundamental theorem establishes a deep, universal boundary, proving that the degree of any algebraic expression dictates the geometric boundary of its coordinate zeros. Today, we have unlocked the beautiful unity of algebra and geometry in the study of polynomials. We traced the classifications of expressions, factored quadratic polynomials algebraically to extract their roots, and proved that these roots correspond physically to the x-axis intersections on a coordinate grid. We verified the fundamental relationships linking the sum of zeros to negative b over a and the product of zeros to c over a. As we observe the rotating algebraic mandala on your screen, trace how zeros, coefficients, parabolas, and formulas spin in perfect mathematical harmony. These elegant relationships form the core foundation of science, driving the calculations of satellite dish focus points, planetary orbits, and dynamic computer code. By mastering these connections, you hold the keys to advanced engineering, physics, and the natural laws of our physical universe.